Okay, this is going to be our fourth video in our electromagnetic induction series. This is going to be our second to last video also, so I should probably mention that the book goes on to do a section on eddy currents. We're not going to be talking about that. We will be talking about the material from 29.7, which is going to be the next video on displacement current and Maxwell's equations. And then we're not going to talk very much. I might make a quick note in that final video about superconductivity, but we're not really going to talk about it too much. So it'll be this video, which is on section 29.5 on induced electric fields, and then one more video on displacement current and Maxwell's equations, which will be on 29.7, and then we're going to move on to the next material that we want to look at. Okay, so for now, let's focus on the material we want to cover in this video. So like I mentioned, this is 29.5 from the text, and it's on induced electric fields. Okay, and so when we think of a conductor moving in a magnetic field, right? Like remember back to when we were talking about the slide wire generator, and we're actually talking about the slide wire moving in the magnetic field, right? So we talk about the slide wire moving in the magnetic field, and we can sort of understand where this induced EMF comes from in terms of magnetic forces, right? As the slide wire moves through the magnetic field, we can see that magnetic forces are going to be pushing charges around in the slide wire, and so we can understand why there's going to end up being an EMF, right? If we place this thing in a generator, we can understand why it's pushing current around the loop, right? But we also know that Faraday's law tells us that there's going to be other situations in which we get this induced EMF or induced current, right? But in this other case, where we're talking about a stationary conductor and a changing magnetic flux through the conductor, it's a little more difficult to imagine the reason why these charges actually move around the circuit, right? Like what is actually driving this? Where we had the conductor moving through the magnetic field, we can see that there's going to be, we've already talked about magnetic forces, we can see there's going to be magnetic forces acting on these charges. But what's acting on the charges in our loop when we don't even have a magnetic field on the loop, right? So let's take a look at a situation here and see if we can build up some intuition about how this is all going to work. So we're going to consider a solenoid here, which is shown below. So we have this blue solenoid. We can see the coil of wire going around it. We pass a current I through the solenoid. It sets up this magnetic field through the center here. If we have a non-zero changing I, right? Like if the derivative of I is non-zero, we have an increasing I, let's say. We're going to have an increasing magnetic field in this direction. And then if we set up a wire loop that sort of goes around the solenoid, we're going to end up getting an induced EMF in this wire loop, right? And there's a few ways we can get at the direction of the current in this wire loop. One way to think about it right away is just use Lenz's law, right? We can see if there's an increasing magnetic field in this direction. Lenz's law tells us that the current that's set up in this loop is going to want to counteract, is going to want to be set up in such a way that it produces a magnetic field that counteracts this changing magnetic field in this direction. And so we can see that our induced current is actually going to run in this direction. But that's kind of beside the point for now. We're trying to get at what exactly it is that's actually causing this current, what's actually causing this EMF, what's driving these charges, right? So so here I've already talked about sort of well, I guess I haven't really mentioned, so our cross-sectional area here is going to be A, and we know that we have n turns per unit length, so this lowercase n we're going to use in this discussion, excuse me, to mean the number of turns per unit length, okay? And so like I said, we're encircling this solenoid in this conducting loop. We have our galvanometer here, which is just another way to say that we're reading the current that's going through the loop. And so what what's the form of the magnitude of this B? Well, if we think back to our discussions in chapter 28, we know that B is going to have the magnitude given by these values here. So mu naught times n, which again is our number of turns per unit length, and I is the current that we're passing through the solenoid. Okay. If we take A, the vector version of A, to point in the direction of our magnetic field, then we have a magnetic flux flowing through the loop, right? Positive magnetic flux. And if we take I to be increasing, if di dt is non-zero and positive, then we have a changing magnetic flux going through our loop. Well, since this is true, we know that we're going to have a changing magnetic flux in this setup, right? We have all those things actually happening. We have our current going through. It has a positive derivative. We've set up our area vector such that it points in the direction of B, and so we know that our magnetic flux simplifies to BA, and we can kind of go back to previous chapters to look at why that is, and this has to be equal to this value here, because we kind of discussed why B would be this value going through a solenoid, right? Okay, so we have our magnetic field going through our solenoid, and I can't keep this picture unfortunately on screen, so just try and keep it in mind, and we'll keep pushing forward. Okay. So if I in the solenoid changes over time, well then our magnetic flux changes over time, right? We can see it from here. If I is changing, clearly our magnetic flux is going to be changing. Okay, and then Faraday's law tells us, if we remember Faraday's law, it's just basically this so far. Faraday's law tells us that if we have a magnetic flux that's changing over time, well, it is inducing an EMF equal to the negative of that change, right? So this is just Faraday's law here. If we substitute in this right-hand side of this expression for our magnetic flux, and we still try to apply the derivative, well, the derivative is only going to hit I here. The only thing that's changing in time is I. I is the only thing that is a function of t. Everything else is constant in time. Our area is not changing. The number of turns per unit length on our coil is not changing. Our magnetic constant here is not changing. So we end up with this expression here, right? We only have one of our variables being hit by our time derivative. Okay. Then if the resistance of our loop, if the total resistance of the loop is R, right? So if this loop has a total resistance, including the galvanometer of R, then we can write the current in the loop as I prime. So careful here, we're selecting to use I prime as the current going through the loop because we've already used I for the current going through the solenoid, right? And they're definitely not necessarily the same. Okay. We could then write an expression for this I in terms of our EMF over our total resistance of the loop plus galvanometer, right? And this is great. We could do this calculation, but we still don't have a sort of a real sense of what it is that makes this charge move around the loop, right? We can't sort of look to the magnetic field. This thing is not even in a magnetic field, right? This loop, there's only really a magnetic field inside the solenoid. There's some residual magnetic field outside the solenoid, but it's so minor that really the magnetic field inside the loop dominates, and we could basically say that this loop is sitting in an area that has no magnetic field, basically. So it's clearly not the magnetic field that's pushing charges around like it was in the case of our moving conductor, right, for the slide wire generator. So what's kind of left, right? Well, it must be that there's an induced electric field in this conductor due to the changing magnetic flux, right? And so I'm going to try to slow down a little bit here. I know sometimes maybe I go a little too quickly through some of this stuff, but this is really one point where I want to take an extra second. It's kind of subtle, right? So how do we know that there's an induced electric field? Well, we know that there's no magnetic field that's doing anything here, right? And there's nothing else that's sort of happening that could cause this. All that there is left is that we know that there's a certain relationship between current and EMF and resistance. We also know that electric fields are related to these, and we can sort of look back through the chapters and see all the ways that these different variables relate to each other. But the only thing that's left that could be getting induced here is an electric field. If there is an electric field, well, then this explains a lot, right? If there's an electric field, there's something causing our EMF, there's something driving our current, and so it must be true that there's an induced electric field in the conductor due to the changing magnetic flux. And this idea is really one more step in a sort of direction that we're going to kind of arrive at a little bit in the next video when we start talking about Maxwell's equations, which are really quite an amazing sort of achievement by physics in their understanding of electromagnetism and the sort of connection between electric and magnetic fields. But I don't want to get too far ahead of myself here, so let's not talk about that right now. Let's focus in on this idea of that there must be an induced electric field in the conductor due to the changing magnetic flux. Okay, and so we kind of talked about this a little bit before, but I'm going to talk about it more here. There's a key difference between electric fields caused by the change caused by the change in these magnetic fields, right? So there's a key difference between these electric fields and electric fields caused by charge, right? So electric fields that are caused by charge give rise to conservative electric forces, right? We talked about this back when we were talking about conservative forces in the context of this course, right? This was in chapter 23. We talked about potential and potential energy associated with our electric field and so forth, right? So electric fields caused by charges give rise to a conservative electric force and what you can think of as a conservative electric field, really, right? And here we're going to see that if we take a look at a charge, let's say we have some charge Q, and it goes around the loop. It goes around our actual loop here, which we have drawn around our solenoid. Okay, so we have a charge going around the actual loop here. And if we take a look, kind of lost my place there. Yeah, there we go. If we take a look at this charge going around the loop, we're going to find that the electric field actually has to do work equal to Q times the EMF on it to get it to go around the loop. So this is doing some non-zero work, right? But if it's doing some non-zero work around a closed loop, well, that means that this electric field, this resulting electric force and thus the electric field cannot be conservative, right? A conservative force can't have work done as you go around a closed loop, right? And so we end up getting this situation where we have this closed loop integral of our electric field dotted into our length elements gives us a non-zero value, right? And so let's sort of take a look at what that integral would give us. Okay, so line integral here represents the work done per unit charge, okay, by the induced electric field. And if we actually do this line integral around the loop, we're going to find our EMF, right? Not super surprising there, right? But because this is true, then we can use this expression, right? We can use this expression with Faraday's law, and remembering that Faraday's law, I think I have it written down just right here. Yeah, so this is the original expression for Faraday's law. So Faraday's law tells us this: if we use this sort of newfound insight that our integral around this closed loop is non-zero, and in fact it's equal to our EMF, well, then we can just substitute in the right-hand side of Faraday's law to get a new sort of formulation of Faraday's law. So this is our new formulation of Faraday's law. We have to be careful here. This new formulation of Faraday's law only applies to stationary conductors, right? So this original Faraday's law applies everywhere. This new version of Faraday's law, this new formulation, gives us useful tools to look at when we're looking at stationary integration paths, but it only applies in the case of stationary integration paths. So when we have a stationary conductor or a stationary integration path, we're going to see that the conductor is not necessarily required. But when we have this stationary integration path, we have this new expression. Okay, so what is this expression telling us? It's telling us again that the line integral of the electric field around this closed loop, so this is our closed loop integral of E dot dl, is equal to the negative of the time rate of change of our magnetic flux. Okay, and so that's sort of our new version of Faraday's law for a stationary integration path. Definitely an equation that we want to box and try to understand, right? Okay, so let's assume that the loop in diagram B, so let's take a look at diagram B very quickly here. So this is our diagram B, and this is our loop. This is the magnetic field generated by the solenoid. This is the I of the this is the current of the solenoid, right? So this is the current running around the solenoid. It's kind of ripping around the solenoid like this. It's producing this magnetic field, which is changing because I is changing, right? So we have an increasing magnetic field going into the page. So we have some changing magnetic flux going into the page, right? And we're going to see that these induced electric field lines really are sort of the way that this electric field is going to end up working out. So let's take a look at the discussion below here. Okay, so we're going to assume that the loop in diagram B on the first page has a radius of capital R. We're going to apply equation 29.10 here. So this equation that we have here, we're going to apply it, and then due to the cylindrical symmetry, we're going to see that E, our induced electric field, is going to have the same magnitude everywhere, right? So we can see that it's going to have the same magnitude everywhere because of the cylindrical symmetry, right? We have every point of this conducting loop is the same distance from the center of our magnetic field. There's every reason to believe that we should have the same magnitude of electric field everywhere around the loop, right? And so, well, I guess maybe another thing to mention here, or we can sort of skip that whole discussion. So let's say that we have our electric field. It has the same magnitude at all points around the circle, and it's clearly going to have to end up being tangent to the circle. There's a couple of ways we can make this argument. The first way to make the argument is it's clearly going to have to be tangent to the circle, because otherwise we wouldn't be driving an EMF, right? Like let's say we had the same magnitude, but all of our electric fields pointed outward like this instead. Well, we wouldn't be inducing an EMF in the loop. We wouldn't be driving a current, right? It would still be symmetric. So the symmetry argument breaks down for the direction of our electric field, but we know we can experiment. And we know that we actually do have a current running around this loop if we do this. Well, that means that the electric field has to be tangent to the loop at every point on the loop, right? So let's go back down to our discussion here. So our electric field is going to be tangent to all the points on the circle. Then our line integral, the line integral which is the left-hand side of our equation here, this is just going to reduce to the magnitude of our electric field times the circumference of our circle. Why does it do that? Well, because E at every point is going to be parallel to dl, right? So as we're going around the circle, if we break this thing up into tons of little dl's, at every point E and dl are going to point in the same direction, okay? If they point in the same direction, well, our dot product goes away. E is not dependent on our integration here. E is the same everywhere, all over the integration, right? So we can pull it outside of the integral, and then we're just doing the closed loop integral of dl around a circle, right? Well, that's just going to give us the circumference of the circle, so we get the 2 pi r. So this is kind of fairly evident that we're going to end up with this result for that line integral, right? So if we take this result and we sort of plug it back into this expression here, we're going to get this expression that we have down here. We have the absolute value sign here because the minus sign that comes along with our time rate of change of our magnetic field can kind of be absorbed into the discussion about the direction of the electric field, right? Here we're only interested in the magnitude, so we're only going to look at the magnitude of our time rate of change of the magnetic flux, right? Okay. So now let's note. So we've done this. We've done this sort of discussion of what the magnitude of this electric field is going to look like for a loop sitting on the outside of our solenoid here. But let's realize that this would be true for anywhere that we want it to be. We could be inside the solenoid. We could be very far from the solenoid. We would always be able to sort of make this discussion or make the arguments that we've made here and come up with the expression that we have here. Okay. So that's sort of the expression for the electric field, which is induced, or at least the magnitude of the electric field, which is induced by our solenoid here. Let's now take a look at what we're going to sort of call this electric field, right? So we've already pointed out that there's a key difference between the electric field that's driving the current in this loop and that's setting up this EMF. We've already talked about how it is a non-conservative electric field where the electric field generated by charge actually are conservative electric fields, right? They lead to forces which are conservative, right? So let's kind of set up the discussion here. The discussion here is going to revolve around non-electrostatic electric fields, and kind of spoiler here, non-electrostatic electric fields are what we call these non-conservative electric fields caused by this induction, right? But let's start off. So we've seen that Faraday's law is valid in two different situations, right? We already talked about this first situation a little bit in the beginning, and we talked about it a couple of videos ago, that the EMF is induced by magnetic forces on charges when conductors move through the magnetic field. This is, again, the slide wire generator. In this video, we spent a bunch of time talking about case number 2 here. So a time-varying magnetic field induces an electric field, and hence an EMF, right? And so we argue that it must be an induced electric field that's actually that the electric field is the thing being induced, and it drives this EMF, which then drives the current that we see going around the loop, right? The electric field is, well, so I mean, I'm just going to state some things that are sort of facts here. We're not going to kind of go through and carefully prove them, but they do stand to reason, right? You can sort of logically follow the argument. So this electric field is induced even when no conductor is present. So it may be surprising, or it may not be. It probably shouldn't be overly surprising, because why should it be that us placing some conductor in this area magically causes an electric field to be induced? The wire doesn't need to be there. There's always going to be the electric field there, whether we have the wire loop around our changing magnetic field or not. So we could get rid of this wire, but it would be hard to measure the electric field at that point. But even if we didn't have the wire here, there would still be, in space, there would still be this induced electric field. And if you drew the electric field lines, they would look like the circles that we see here, right? We would see a circle, and at every point we would have our electric field pointing in the same direction that it does here. Okay. So there really is an electric field being induced whether or not there is a conductor present. Okay. The electric field is, as we said before, not an electrostatic field. It differs from an electrostatic field in that it's non-conservative, right? And when we talked about this argument, it's non-conservative because I guess it's kind of a circular argument. These are both true because the other one is true, but it's certainly true that it's a non-conservative electric field because the loop integral around this closed loop is non-zero, right? We would need that loop integral to be zero for this to be a conservative electric field, for it to give rise to conservative forces, right? Since it's non-zero, it's non-conservative. Okay. We talked about this before. So when a charge moves around the path, the field does non-zero work on it, right? And so that's, again, just another statement of this expression here. And this means that the concept of potential energy has no meaning for this kind of a field, right? We can only define potential energies for forces which are conservative, right? And the electric field can be thought of as a sort of intimate brother of the force which well, of the electric force, right? You can kind of see the expression down here. So if a force is conservative, well, the field that gives rise to that force is conservative as well, right? And in this case, our force is non-conservative, our electric field is non-conservative. We call these fields, or this specific type of induced electric field, a non-electrostatic field, right? So this is a non-electrostatic electric field, okay? Although, I should probably still point out this last point here. Although this is a non-electrostatic field, it's still true that this expression holds. This non-electrostatic field, even though it's non-conservative, still gives rise to an electric force. So if we have some charge Q in this electric field, it still gives rise to an electric force. If we had this wire removed and we had a changing magnetic field just as we do here, and we place some sort of a test charge here, well, it would act just as though it was sitting in the electric field pointing in this direction, right? It really does exert an electric force, okay? Okay, so there's a lot of sort of subtle concepts in this chapter. I would, well, maybe not even in the whole chapter, just specifically in this section. So I would recommend maybe just a quick read through the notes if you guys have time. I'm going to move on, and I'm going to do a quick example here. And this is the wrong example. What have I done here? Okay, hold on. Let me see if I can fix this. Yeah, okay, so I just haven't changed the title. This is actually 29.11. This is the title from the example we did in the last video. So I'm going to cross that out. That is not correct. We're actually going to be doing induced electric fields. Okay, so that's the correct title. This is actually the correct problem, though. This is directly from the text. This is their 29.11 induced electric fields. And so we're going to take a look at the following situation that we have here. Okay, suppose that the long solenoid in figure 29.18a, that's actually this figure that we saw up here. So we're thinking about this diagram here. So suppose that solenoid has 500 turns per meter and a cross-sectional area of 4 centimeters squared. Excuse me. The current in the windings is increasing at 100 amps per second. Okay, and in part A, we want to find the magnitude of the induced EMF in the wire loop outside the solenoid. Then in part B, we want to find the magnitude of the induced electric field within the loop if it is a radius of 2 centimeters. Okay, so we're going to take a look at both of those. I have some numbers worked out for this here, so let's hope that they work out. So in part A, what do we have going on? We are looking for the induced EMF, right? The magnitude of the induced EMF. Okay, so we know that Faraday's law tells us that the magnitude of the induced EMF is simply going to be equal to the negative of the timed rate of change of our magnetic flux, right? And we talked about just before how for a solenoid our magnetic flux can be written as the expression we saw a little while back, right? So it can be written like this: mu naught N A I. Okay, and let's remember this is our magnetic constant. This is our number of turns per unit length. This is the area, the cross-sectional area of our solenoid. This is the current running through the solenoid. Okay, and like it was above, excuse me, like it was above, we only have one thing changing with time. So I can move that derivative over, and we end up with di dt. Okay. And so now we can just straight substitute numbers in. We know what di dt is because it's given to us here. We know what the time rate of change of our current is, so we can just substitute that number in. We also know what the area, number of turns per meter, and so forth are. We can just substitute in these numbers, and we end up with a minus 4 pi times 10 to the minus 7. This is our mu naught. We're told 500 turns per meter. We need our area in meters, so that's going to end up being 4 times 10 to the minus 4. That's our area in meters, where it was 4 centimeters squared. And then we need our time rate of change of our current. That's going to be 100 amps per second. If you plug all that into a calculator, you end up finding that we have an EMF, it's not that good, EMF of minus 25 times 10 to the minus 6 volts. Okay, I have a pretty small EMF induced here. Okay, then in part B, we want to answer the question, we want to find the magnitude of the induced electric field within the loop if its radius is 2 centimeters. Okay, so to find the electric field, we can use our new formulation of Faraday's law, which we have to remember only applies to stationary conductors. Okay, so in part B, we're going to make use of this expression, okay, which is equal to this. Okay, and this is just 29.10, that new fancy equation that we wrote down a couple of pages ago, right? But we know that Faraday's law just tells us that, well, this is just equal to our induced EMF, right? So that's great. And the symmetry of the problem hasn't changed. So this integral that we're going to have to do, this line integral around that loop, is exactly what we talked about before. It's just going to exactly end up being, it's just going to be the magnitude of the electric field, right? It's going to be the magnitude of the electric field times the circumference of the circle. It's the same integral again, and we have the same symmetries, so we can make the same argument here. Now, it's not necessarily true that you will always have those same symmetries, but if you're dealing with a cylinder, and oftentimes when you're dealing with a solenoid in this sort of cross-sectional view, you do have the cylindrical symmetry. Well, you can just right away say, well, E is the same at every point on this thing, so you don't have to integrate over E. And integrating over dl around a circle just gives us back our 2 pi r, right, like usual. So the two of these are going to be equal, and we want to be a little bit careful here because we've kind of gone from talking about E in terms of a vector to talking about it in terms of a scalar, in terms of a magnitude. We don't really care about this sort of minus sign. We're just going to think about this induced EMF as an absolute value. It may have a minus sign, and that will have some effect on which direction our E is pointing, our electric field, our induced electric field is pointing. But in this case, really, all we care about is the magnitude of our induced electric field. So we can just isolate E here. E is just going to be the magnitude of our induced EMF, which we calculated above here, over 2 pi r, right? And again, we can just substitute in values, so we're going to get 25 times 10 to the minus 6, and I've dropped the minus sign here, right, because we have our absolute value. We're only looking for magnitude, over 2 pi, and this is going to be our new radius, which we need in meters, so 2 times 10 to the minus 2 meters, right, because it's 2 centimeters. Do that calculation, and you're going to find the magnitude of your induced electric field of 2.0 times 10 to the minus 4 volts per meter, right? Okay, so that is our electric field magnitude, which is induced by this changing magnetic flux. Okay. All right, so I will leave this one here, and like I said, we're only going to have one more video for this section in which I'm going to discuss displacement currents and Maxwell's equations. It kind of ties together a lot of interesting ideas, and we're kind of getting closer to the end of the course here, where we're really going to get to the sort of punchline where we bring together all these ideas and hopefully have time to tie together electricity and magnetism and really kind of get a look at Maxwell's equations and kind of have a chance to work with some of this a little bit. Okay, so I'll leave you guys here, and I'll see you in the next one.